In the year 1792, the Scottish engineer, William Murdoch, presented to the world his latest invention, an invention which was to have a huge impact on society for the next 100 years at least. He presented the world's first portable illumination source using a gas. And underneath his arm, which is what I have here, he had a gas bag. Now, what I'm going to talk to you about today is what this gas is, where it has come from, the impact that this invention had on the world, and all the side effects. But before I do so, we must first of all light our candle. This is not the purpose of this gas. The purpose of the gas is to actually provide light. But as you know, flames also provide heat. I'm now going to ask dear Andres, my friend, who is helping me today, to extinguish the flame and take the gas bag from under my arm. Thank you very much, Andres. There we are. We have to take precautions. And now, the gas, of course, thank you very much. We have the lights. The gas, of course, the gas which that William Murdoch was burning was coal gas, a gas which had been derived from coal and which indeed people had already noted some time ago, but they didn't recognize what it was. Now, what I have to tell you is that towards the end of the 18th century was a great period for the evolution of science, where the concept or the idea of substances which were gases was very new indeed. People had for many, many centuries talked about different kinds of air, but gases as individual substances had been developed by the English school of chemistry, especially with Joseph Priestley, who was a brilliant manipulator of gases. Today we shall be manipulating some gases. Let's go back to coal then, and how did this situation arise? Well, coal is one of the fuels which mankind has used for many, many thousands of years. And I'm just going to hold up a few pieces of coal to prevent my hands from getting dirty. Obviously, I prefer to get some gloves dirty. So here we are, and start off with a piece of this is the sort of fuel that for thousands of years has been known to humanity to provide a fantastic source, above all, of warmth. But what is coal exactly? Because it looks like this. You take a lump of coal like this, it's been mined, and it looks like a single substance. That, you see, is a great misunderstanding. It is not actually a single substance. It is a very complex mixture. Coal has been derived from the compression of vegetable material, especially trees, over a period of millions of years. Dead trees during the Carboniferous period, that's what it's actually called. The trees that grew on this planet were compressed by layers of rocks in the absence of air, and they ended up forming huge deposits of this black substance, which, as I will show you shortly, burns. So I'm started off by telling you that coal is not a single substance, which it appears to be. It is actually a mixture. I'll very briefly tell you what it's comprised of. The main part of coal is the element carbon. And I have here a pure sample of carbon in the form of graphite. Now, this actually, as you can see, resembles coal, but it's considerably shinier. And it has a shiny appearance here. So that is pure carbon, the main element present in coal. And I ought to tell you that there are several different types of coal, which when they burn and when they react chemically, produce significantly different types of results. And I wanted to say that this specific type of coal, which I've got here, is bituminous coal, which contains about 85% carbon. So this is pure carbon, that's 100% carbon. This contains about 85% carbon. Here I have a briquette of modern smokeless fuel. This is compressed anthracite, and this contains about 95% carbon. So what are the other percentages made of? Well, in bituminous coal, there are a large number of substances present, and the elements are rather than telling you which substances, I'll tell you which elements are present. There will be the elements hydrogen, oxygen, nitrogen, sulfur, arsenic, tin, arsenic, lead, for example, and iron. Those are the principal elements present in the coal as well. And but rather than going into the theory, let's first of all see how a sample of coal burns. So I'm going to set this sample of coal on fire, and then we're going to see how it ignites. Now, for this purpose, of course, I'm going to be using a little bit of modern technology like this, and this is how people will have observed coal burning for many, 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 many thousands of years. And I'm sure you can all see the first thing you notice is a foul smoke. And that, my dear friends, is of course pollution. You don't get something for nothing. There is our coal on fire, but you see at the same time a huge cloud of very unpleasant smoke was produced. And this, of course, this very unpleasant coal smoke is, of course, pollution. And that is one of the main problems which people have been confronted with in using this fuel. Now, that pollution consists of smoke, which produces soot. When you burn it in a chimney, for instance, you burn in a grate rather, the smoke goes up, and it consists of a multitude of substances, which we are going to very shortly subject to some simple analysis. But one of those substances is soot. Now, I do have a jar of soot somewhere here. Here it is. Here's my jar. Just to show you, this is normal soot which came out of a chimney, and I'm just going to pour a tiny amount. It's a foul black substance. There it is. That's chimney sweep soot. And you say, well, what is this? Well, it's a complex mixture of very, very potentially hazardous substances, obviously made up of carbon. But one of the great things about human beings is they're very ingenious. So I read in a very recent newspaper article, just literally a couple of weeks ago, that soot can be used to repel slugs in your garden. So if you're a chimney sweep, for instance, and you have a huge excess of soot that you've just collected, you sprinkle on your garden, and you can be reassured that slugs will not attack your cabbage and your various other vegetables which you're growing. But the ingenuity of the human is such that I can assure you that scientists will have found other uses for soot like this. Now, I am now going to, therefore, proceed to the process of burning some coal and analyzing the products which are produced. And you see I have an apparatus set up here. I am going to very shortly bring this into action. And I'm going to ask, first of all, Oscar, who's my son helping me today, to come on and start off our bellows. We're going to, first of all, we're going to be burning the coal in here. And we're going to be burning it by passing air through it using a very, very ancient type of device, which is called a bellows. And bellows have been used for thousands of years. And please, when Oscar pumps the bellows, I'm going to explain what happens. He will generate a flow of air, which will go across the coal in here. I will be strongly heating the coal there, and the products of the combustion will go through 3 Dreschel bottles. And these 3 Dreschel bottles will contain, in turn, here is lime water, which detects carbon dioxide. It turns milky, which is the main product of the combustion of coal. Here I have some universal indicator dissolved in water, which will show you whether the products are acidic or alkaline. And here I have some potassium permanganate solution, which will tell you something a little bit more about the nature of the product. Now, I want to be quite frank with you. The object of this is to show that acid is produced when the coal burns, and the specific acid we're looking is sulfur dioxide gas, which reacts with water to make a solution of sulfurous acid. So, Oscar, could we first of all test the pneumatics and see that air is indeed going through all 3 bottles? So you can see here the air is bubbling through, so the system is working. And I wanted to tell you that at the same time as I'm doing this experiment, which will last approximately 10 minutes, I'm going to ask Andres to come on and do another experiment by heating coal, which initially looks to be exactly the same. So please look, here we have coal powder, it's going to be heated. Here we have lumps of coal, which are also being heated. But there ends the similarity, because in this and they are both going to undergo a chemical reaction. But in this particular case, because we're passing air over the coal will combine with the oxygen from the air in a process which is called combustion. Here, though, because there is no air being produced, etc., the coal will chemically break down into different substances. And we have here the tube which will be collecting the product there, and which will be collecting a liquid product. There is some water in there to help to condense the vapors, and there will be a gaseous product coming out of the top there. Andres, just one little thing. We may have a problem in getting a constant flow of gas if that's bubbling all the time. So maybe see how it goes. But if we don't get a constant flow of gas coming out, then we will. And this gas, by the way, is going to be the gas I was burning at the beginning. It is known today as coal gas. Then it was called illuminating gas. And illuminating gas, as I said, was a major topic of research for over 100 years. And even today in London, there are 1,500 gas lamps burning on our roads. But the flame is slightly different from the flame that we have here due to a little bit of chemical science that we have improved things. So I'm going to ask Oscar to start pumping. I will now start the heating process. And Andres, if you wouldn't mind kindly getting this. Now, this takes about 7 or 8 minutes. So if you could kindly start heating, Oscar. I am now start pumping, sorry. Oscar's pumping, and I am now heating the coal, and I ask you to watch carefully. Notice a little bit of water vapor condensing there. Start to look to see if you could see any changes in any of the liquids. There will be a lot of smoke produced in this, and I think we're on fire. I think we're on fire. Keep going, Oscar. We have a flame almost certainly there. This will last for at least 5 minutes, by the way. Let's see if we can take, that's it. Keep it going now, Oscar. Now, the trick is we have a critical mass of coal which is burning there, and that should sustain itself. Andres, could you kindly start the process there of roasting that? Now, we have here 2 different types of chemical process. This one here, where the coal is burning, keep pumping, Oscar. It is giving out heat energy. It's glowing red hot, and it's giving out heat energy as it is combining with the oxygen from the air. Here, though, we have a process which is endothermic. There is no oxygen passing over, and there is no chance at all for the coal to catch fire. There is no air there. So this is an endothermic process. Here we have an exo. I'm just going to heat it a little more just to make the... Please notice the colors will shortly start to change. I'm going to, as I said, this does take about 5 or 10 minutes. It's not an easy experiment to do. Shall we get Clara to help? Clara, could you come? My daughter Clara, I have asked to keep the flame going because it doesn't always keep itself going. Keep going, Oscar, keep going. I have to be careful not to heat too strongly, otherwise the tube will melt. Are you okay there, Oscar? I'm trying to get more coal to burn in order that we can get the relevant changes in the colors of our liquids. And I hope you can already, that's better, Oscar. We've got a roaring flame in there now. Not too far, otherwise you'll set the bung on fire, Oscar. We have to take care. Now, please notice, the color is going yellow. This shows an acid being formed. The color here we're getting clearly is going milky, showing the formation of carbon dioxide. This is very good, Oscar. We've now got a proper fire burning. I'm going to warm myself up on this. Please excuse me. Very good, Oscar. This is a nice glowing fire by the coal side, etc. But please note, look at the amount of smoke that it's producing. And this is the problem. Not only the smoke, but please notice, this solution, potassium permanganate acidified, is now changing in color from pink to almost colorless. It will shortly lose its color. This solution here, keep going, Oscar. You're doing very well. Sorry, I have to keep it's very hard work doing this, by the way. Oscar's been doing weight training to keep himself fit for this for the last 3 weeks. They're doing very well, Oscar. You notice this is now going yellow. I might give it this. We now have loads of carbon dioxide, which I said obviously is going to come off because that's the main product. Now, we have here red hot, and you notice, and the flame, Clara's trying to keep it sustained, and it will occasionally burn. Now, that is illuminating gas, and I will explain to you exactly what that is in a minute. In here, though, we have coal tar, which is collecting that a few droplets of a black liquid there. The idea is to try and keep it going without it going out. Now, here you see we've almost lost our color there, and my trick is to try and get this to go red, by the way. And the reason is because sulfurous acid formed in this reaction by the sulfur impurities is capable of turning the universal indicator red. So I'm just going to give this a little booster. I'm just going to give it a little booster to get the fire burning again. We're aiming for red, but it does take a while because at the end of the day, there is not that much sulfur there, you see. There is not a great deal of sulfur there, and we will hopefully get it to turn red. So Oscar, keep going. We're succeeding there. I think that one, we're about to blow a hole in this one. So once we've blown a hole, that means we've blown the whole experiment. So I have to take great care not to overheat locally. Not to overheat locally. Keep watching to see. We're getting close to red now. And we're hoping for colorless on the other one. As I said, there is not a great deal of sulfur present in the coal, up to 1%. Now, the next question which one may ask is, how is this sulfur present in this coal, which looks like a single substance, but is not, in fact, it's a mixture. So we're continuing to keep going, Oscar. We'll just give it a little bit more. It's going red almost now, and the other one is almost going colorless. So we're getting a result. Oscar's out of breath. I'm sorry. Okay, still, Oscar. Thank you. We're very close, Oscar. Look, we've almost got the red, which is caused by sulfurous acid coming from the sulfur impurity, acid rain, basically. And here we've almost gone colorless, and that shows that there is a reducing agent present. This reaction proves that, Oscar, we're very, very nearly there. We have a red color, so we've now definitely acidified our water, which was there, and this one has almost given up the ghost. Oscar, pump more. That's it. Keep it. I'll tell you what, I'm going to block the end of the other one with my finger to get more to go there. That's it. Now keep going, Oscar. We're very nearly colorless. Oscar, brilliant. Thank you. We'll call it quits there. Thank you very much indeed. Now, we've made a huge amount. We've made a huge amount of smoke in here, and we've caused a lot of pollution. And I've warmed my hands up, but I must say it's a heavy price to pay, all this pollution we're now sitting in order just to have a bit of warmth. And that, you see, is one that has forever been the big problem. Various laws have been introduced for hundreds of years ago already to prohibit the burning of coal because of all the unpleasantness. Now, I wanted to start off with by returning to this solid lump of coal, which looks like a single cell. So how on earth is sulfur present? Well, I'll tell you. A tiny amount of this has got this inside it, which is iron pyrites, iron sulfide. And I have here a perfectly grown crystal, because iron sulfide, when it's pure, forms beautiful cubic crystals. And this is some pure iron sulfide. And the question which you may ask, therefore, if you were to heat this in air, would it make sulfur dioxide? The answer is yes. It will actually chemically combine with air, and it will make sulfur dioxide, and it will bring about these two effects: potassium permanganate acidified, going colored, and the universal indicator turning red due to sulfur dioxide present. Now, some of the sulfur is present in the form of pure sulfur, uncombined, and these huge deposits occur in the Earth's crust. And here we have some sulfur crystals, you see, this is rhombic sulfur here, and they occur, and we extract the sulfur by mining, still on a very, very large scale today. The other compounds of sulfur which are found in coal are organic compounds made of carbon, hydrogen, sulfur, oxygen, and so forth, and they are present in here. So this remarkable substance, coal, which on the face of it appears to be one substance, is actually a mixture. And you see, which was chemists who devised the supremely useful way of classifying substances as elements, compounds, or mixtures. And here we have, you see, the element carbon, which is approximately 85% in this bituminous coal. Then we have a variety of other substances, and this is an example of a compound, iron sulfide, pyrites, formula FeS2, and this inside here is mixed together with other substances: mixture, compound, elements. So this mixture, these substances I'm showing you in a splendid manner illustrate exactly what coal is all about. Now, the next thing I wanted to show you is when the coal has burnt in there, of course, it's made these gaseous products, but we must not forget that there is a solid left behind, and that solid is ash. And I have some ash here, and it's a horrible stuff. It comes out of, people always throw it away, etc. And I'm going to show you now that this ash actually here is quite an interesting substance. And as I said, what use can you make with coal ash? Not a huge amount comes in. And I'm going to tell you that coal ash actually is made up of principally three oxides. Silicon oxide, silicon, by the way, I forgot to mention there, aluminium oxide, iron oxide, and calcium oxide. Now, I'm going to spoon some into here. I'm going to spoon some into my filter paper there. This is quite a messy ash from a fireplace. And I'm now going to show you that if we pour some universal indicator through this ash, which I've got there, then you will see, hopefully, I'm not sure that this will definitely work, but we should see a slight color change. And that will tell us something about the nature of the substances, as I told you, made up primarily of iron oxide, silicon dioxide, aluminium oxide, and some calcium oxide. And we're going to, this takes a little while. Dear Andres, could I ask you to just pour that through, and I'll continue. If you just carry on pouring that, please note the color change. Now, I wanted to turn a little bit to what I've got in here. There was water there to start with, but there is a black, dark brown deposit there. Now, for many years, or when people started doing experiments with coal and understanding the idea of a gas and a liquid and a solid, the three states of matter, which also, those ideas have played a huge role in our understanding of the behavior of matter, people started, what a horrible black mess, let's throw it away. And they did. It had a foul smell and a foul appearance. But this coal, this tar which I have here, which is correctly called coal tar, obviously, is a most remarkable and complex mixture of several hundreds, if not thousands, of substances. And we, as chemists, have helped us to make use of that. Thank you very much, Andres. And you will notice as the universal indicator comes through, this is not acidic, but this is a slight alkali. You should notice the color being a beautiful ultramarine blue. Now, the reason for that is, as I told you earlier, out of those oxides which are present in coal ash, one of them is calcium oxide. And calcium oxide is alkaline. It gives the alkaline reaction with water, forming calcium hydroxide, and it's present in tiny amounts, but sufficiently large amounts for the indicator, the universal indicator solution, to turn from green to blue. Now, I am going to return to the coal tar in just a few seconds, but I just wanted to go a little bit onto this gas which you saw burning, illuminating gas, as it was called by William Murdoch, and which set off a complete revolution in the way lighting is affected. For thousands of years, people used to burn candles or oils, etc., to provide a source of illumination. And if they wanted portable illumination, they would have a torch with a wick at the end, soaked in oil, and that would then, you could carry this torch around. But what William Murdoch showed is the use of a totally different kind of substance to provide light. And that substance he called illuminating gas, which he had made from the distillation of coal. Now, this process, which Andres demonstrated to you here, this process which Andres had demonstrated is technically called the destructive distillation or the pyrolysis of coal. Pyrolysis means heating in the absence of air. Destructive distillation means breaking down molecules into smaller molecules. So you had large mixture of molecules present here. On heating, they split up. Now, I'm going to tell you a little bit about the types of molecules which are present. You see, the majority, I hope you understand, the majority of the compounds that we're dealing with with coal are compounds of carbon. Now, when carbon is present, or when substances are released from this distillation, pyrolysis of coal, the carbon is frequently mostly combined with hydrogen, which is another element which is present in here. And I wanted to tell you that the substance which is the most simple compound of carbon and hydrogen is methane. Methane has the chemical formula CH4, and it is the gas which comes out of all of our gas taps today. Natural gas, what we have burning out of our gas taps, is mainly methane. It's 99% methane. It comes out of the ground without any treatment. It simply comes out. Now, the coal gas, which comes out here, is a mixture of gases. What you saw burning there, what Clara was burning, you saw that momentarily this yellow flame with quite a bit of smoke coming off, is a mixture of gases, of which the main component is actually hydrogen. Hydrogen gas, about 45%, and then the second most common gas there is methane, CH4, and it's about 35%. The coal gas composition does really vary quite a bit on how high the temperature is, what coal you started with, and how long you were heating the coal for. So that's the simplest gas that carbon forms with hydrogen, and that is natural gas methane. So where does the illumination bit come from? Well, in coal gas, which is a mixture of gases, about 5% of the gases are actually slightly more complicated molecules. I will just very briefly explain. Carbon is the unique element out of all the elements that is able to form more compounds because it can form long chains of itself, more compounds with other elements, but very typically with hydrogen, than all the other elements put together. We are substantially made of carbon. We're all made up of organic molecules, huge organic molecules. There is a lot of carbon in all of us. So when carbon combines with hydrogen, it makes compounds which are called hydrocarbons. And methane is the simplest of these, formula CH4. Now, the next longest molecule is C2H6 ethane, and these two burn pretty much the same. But the illuminating part is produced by compounds of carbon which have double carbon-carbon bonds in. And this chemists have recognized today. This is a molecule of ethene, C2H4. This is a molecule of ethane, C2H6. And it's that small percentage of the illuminant gases, ethene, acetylene, C2H2, or ethine as it's known today, which give it the luminosity. I'm going to return to that later on. But in the meantime, I want to return back to our pollutant, the sulfur. And I wanted just to show you a few experiments, because we saw it took about 10 minutes there to get those colors to change, or several minutes. I am though going to now to actually ignite some sulfur and make some pure sulfur dioxide. And the way I'm going to do that is by burning some sulfur. Could we have the candle over here? Thank you very much, dear Andres. Now, what we're going to do is this. I am now, thank you very much, if you just put it over here, I am now going to ignite some sulfur, and I'm going to burn it in pure oxygen. Now, the reason why I'm doing is it does actually make a very, very magnificent flame. Now, to do this, what I'm doing is I'm simply putting some, this is crushed rolled sulfur, and it is sulfur which has been finely powdered. You can get flowers of sulfur which have a more loose arrangement. And I'm going to ignite the sulfur on my candle here, and then I'm going to lower it into this flask. Now, this flask is full of the gas oxygen, pure oxygen is in there, and water with a bit of universal indicator. Please note the color, it's green. What I'm going to do now, I'm going to set this on fire, and I will ask for the lights to be switched off from now on, please. So if we could have the lights off, because then you will be able to see how this reaction proceeds. So we're going to now lower our, we're going to set the sulfur on fire. Now, this takes a couple of minutes. If we were to use one of those powerful burners, then this would happen in a course of a couple of seconds. But I do want you to show that we could use the trusty candle as a source of light, as a source of heat, in addition to a source of... nowhere near ready yet. Sorry, I've got to thank you very much, Andres. Now, what's happening? The sulfur is now melting. It's melting into a brown liquid. It melts 113 degrees centigrade, and very shortly, it will catch fire and burn with a flame which you can barely see. There it is. It's not yet. We'll just wait just to see. You can barely see that flame. There it is. Please watch carefully as I now lower it into pure oxygen. And you will see the sulfur now continues to burn with a brilliant blue flame in there, you see. And as it does so, it's giving off a white sort of smoke. That is the gas, sulfur dioxide, which is the main pollutant, which is produced in tiny amounts, as you saw before, when coal burns. And that has been a source of a considerable headache for many, many years, but chemists have now championed this. And when coal is burnt in industrial, for instance, in coal plants for producing electricity, the sulfur dioxide is removed by combining it with alkaline substances such as a lime slurry. Now, by the way, going back to the ash, because ash does contain lime, what is ash used for? It's used in the building industry for making bricks and cement and breeze blocks. So I will be slightly hovering backwards and forwards just to keep you posted. But the honest truth is, we as humans are terribly inventive and we waste nothing. But it's always a challenge, and the chemists play a great role in this. Can we have the lights back on, please? I'm now going to swirl around my water in there, and you'll notice it has now turned to the red color. Now, that red color, of course, shows us the formation of an acid. Not yet, not that now. Now, what I'm going to do now is this acid which I have made in there is very, very unpleasant. Sulfur dioxide is an extremely unpleasant gas. It causes asthmatic attacks, and I'm not too good. And I'm now going to squirt ammonia in to neutralize. Now, ammonia is a strong alkali. Now, it will neutralize it. It may catch fire as well. You'll see dense white smoke going on. Acid plus alkali makes salt plus water. If you see a flame, don't be surprised. It doesn't have to be a flame. The flame would only happen if there's any oxygen left in there, because the ammonia will catch fire. But what I'm doing, I'm essentially neutralizing this most unpleasant acidic gas with an alkali, which is sodium hydroxide. And once I know I've got enough in there, then the universal indicator will turn back to green or even to lilac if I have an excess of ammonia. So that then is the demonstration for sulfur dioxide. Can I ask you to take this away, please, Andres? Thank you very much indeed. The flask gets quite hot. No, this is not here. Now, what I've got here are two more jars, just to show you. Sorry, I have to take care not to burn myself, just very carefully. These gas jars both contain sulfur dioxide, and I will now demonstrate for you very quickly two reactions to show it's a reducing agent. If we pour in some acidified dichromate solution, this is a standard test for a gaseous reducing agent, or a reducing agent. Andres, can I ask you to kindly take off the lid, and I'm going to ask you to watch the dramatic color change. It turns from orange, and I'm sure you'll know what color it makes as I pour it. Just take it off. There we are. And there, just hold it up for to put the top back on. Thank you very much. So that's the first change. That's showing only sulfur dioxide will give you this reaction from orange to green. And this one you've seen already. This one here is the one which took us about 5 or 6 minutes when we were burning the thing. But here, we will now do it with pure sulfur dioxide. Now, sulfur dioxide, as I said, it's a powerful lung irritant. It's a very unfair, but we have fantastic ventilation here. So that's why we're able to do these experiments here in relative safety. So pour this in, and you'll notice it goes completely colorless instantly. Now that, once again, both of those experiments illustrate the fact that sulfur dioxide is a powerful reducing agent. You may like to know that it is for this reason that it is present in many foodstuffs. For instance, dried apricots, lots of wines, and also ciders are at least those which I know, if you read the label, they contain sulfites. The sulfur dioxide is SO2. When it dissolves in water, it forms sulfurous acid, H2SO3. When you neutralize it, it then forms sulfites, SO3, 2-. Having shown you some experiments, let us now return. So we've had a brief look at the products here. Coal, when it burns, makes ash, which is a mixture of oxides, and you see they have a slightly alkaline character. We've examined the carbon dioxide and the sulfur dioxide here. That is the burning of coal, or the combination of coal with oxygen. We're now going to just turn our attention back to what we had here. We heated the coal very strongly in the absence of oxygen, of air, and we have a solid product left in here. We have a liquid product which is left in here, and a gaseous product which is left in here. Now, all three of these have contributed hugely to the benefit of mankind. The destructive distillation of coal is one of the most useful processes that human beings have invented, because all three products have played and continue to play a most important role in our everyday lives, which we perhaps seldom stop to think about. I'm going to start off by showing you this one here, and I'm going to tip out the solid product here, and you look at that and you say, but hang around, that looks exactly the same as what you started with. Don't look at the powder, it's these lumps. Now, these lumps here are essentially, and I've made a few more here, they are a substance which is called coke. It is essentially, it's a smokeless fuel, and indeed, this here, which is crushed anthracite, which is about 95%, it's a high-grade carbon fuel, which emits very little smoke, has practically the same as this. Coke, this is very light. If anyone wants to come and hold this, it's certainly much lighter than the coal I start, and it's quite porous. And the reason is, you've driven off the tar and the gaseous product by the action of heat. Now, coke plays an enormous role in our lives, because when this process was first developed on an industrial scale in the latter half of the 19th century, the coke was started to be produced on a large scale, and immediately it was used on a very large scale for steel making. And today, indeed, you learn at schools in the blast furnace, one of the 3 solid ingredients is coke, which acts as a powerful reducing agent. I will return to coke in just a second. I'll tell you another use of coke, because I'm going to go on to tar next. Another most important use of coke was the manufacture of calcium carbide. Now, at the beginning of the 20th century, we started developing techniques for making very high temperatures in furnaces, electric furnaces. And what they were able to do was they realized that if you roast coke, which is essentially pretty pure carbon with just the ash impurities, and you roast it with calcium oxide, what we find here, but obviously in tiny amounts, but calcium oxide is relatively easily obtained from chalk or limestone simply by roasting it. If you heat coke with limestone, you end up with coke with calcium oxide or quicklime, you end up with a substance which I'm going to pour on my fingers here, which is called calcium carbide, a few lumps of calcium carbide. Now, calcium carbide looks fairly innocuous here. It was used for some time. It was used for the manufacture of calcium cyanamide by reacting it with nitrogen, and then for producing ammonia. But that was not necessary, because ammonia, believe it or not, when you actually do this coal tar production here, if I was able to get to 1,000 degrees centigrade, which we can't in these circumstances here, then one of the important ingredients there is actually ammonia gas. That's made from the nitrogen components of this, and that ammonia then forms what we call an aqueous layer above the tar, and that was a main source of artificial fertilizers, which was so important for the feeding of humanity, the rapidly growing population towards the end of the 19th century. So coal tar had as one of the very important products ammonium compounds and ammonia, which is obtained through the distillation of bituminous coal at about 1,000 degrees centigrade. One of the other extraordinary things that I have learnt as I've prepared for this talk is, depending on what temperature you heat the coal at, what type of coal it is, and how long you heat it, you get a remarkable different range of products. But the industrially used temperature was about 1,000 degrees centigrade, because that then not only gave you that tar, but it also gave you the aqueous distillate containing ammonia. Back to our calcium, to our coke and our calcium carbide. Now, calcium carbide is a very interesting substance, because it links inorganic chemistry with organic chemistry. Organic chemistry being the chemistry of carbon and its compounds. And I wanted to start off by showing you the chemical equation. I think it's very important that during a chemistry lecture we should see at least one chemical equation. So could we have it, please, just up on the slide? There it is. Now, there it is, and children, you should, if there's one equation I want you to learn that today, it's first we start with a word equation. Calcium oxide plus carbon makes calcium carbide plus carbon monoxide, which is a colorless toxic gas. And then we have the balanced chemical equation, which I've written below. Now, what's slightly unusual about this is when you learn your reactivity series at school about the relative reactivities of different metals, of different elements, normally oxygen is far more reactive than carbon. But when you do this reaction at 2,000 degrees centigrade, the whole process is reversed. The carbon becomes more reactive than the oxygen, stealing the oxygen, as we say, from the calcium and leaving behind calcium carbide. Now, calcium carbide was to play a fundamental, and it was a blockbuster invention, because this put a new light altogether on illuminant gases. I'm going to ask on Oscar to make some calcium carbide now by reacting it with water. I have here some calcium carbide, and I'm going to ask Andres, in the meantime, to put into action 2 lamps, because calcium carbide was used for illumination purposes, as I've said, and this was a significant step up. Oscar, could we get going? We're doing these 2 experiments simultaneously in order that we can show what's going on. So please focus on both. Now, there are your things. Oscar is now, what's Oscar doing? He is adding water, pure water, tap water, very gently onto some, and you'll notice bubbling in our pneumatic trough. There we are, very gently, Oscar, 1 drop at a time. It's quite difficult to control this, by the way, because the reaction is very, very rapid indeed. And there we are. So bubbling now. Oscar, can we test the gas? First, test it just to see that it's pure acetylene. Acetylene burns with a very bright yellow flame, producing clouds of soot. So don't be put off by this. The soot is pure. Just test it first. And there it is, just a little more. It's coming off pretty violently, Oscar. Perhaps we could just turn the tap down a little bit. We haven't had much practice at this, but Oscar does like fire like myself, so I'm sorry about that. We are pyromaniacs on the choir. Now, Oscar, if we can collect the gas, please. Collect the gas by passing over. In the meantime, what Andres has done, he has set up 2 acetylene lamps. Now, one of these acetylene lamps was used by miners for illuminating when they were deep underground, which is a most curious habit, as I will very shortly explain. And the other type of lamp, which I have here, is in fact a lamp that was used by cyclists. And both of them give out very, very beautiful flames indeed, as I hope you will shortly see. We have not practiced these experiments a great deal, and I'm hoping that it takes a little while, but I think Andres has more experience of these than I do. So Oscar's now going to he's collecting a couple of gas jars of the acetylene, and then he will set fire to them. Now, what's important for you to understand, that he will be igniting pure acetylene. There's no air mixed in with it. And when we ignite pure hydrocarbon gases, then we have a phenomenon called incomplete combustion. The gases burn, but with a smoky flame, a yellow smoky flame. So here you have a candle burning with a yellow flame. It's not giving off a great deal of smoke, but nevertheless, that's a process of incomplete combustion because some soot is produced, as you know. Oscar, could we now kindly try and see, I hope you've turned that off already. If you haven't, thank you very much. So now could you just ignite a couple of jars, the tube jar? So here we have, while Oscar's, here we have, this is now, can we have all lights off, please? This is very beautiful. I want you to see this magnificent cycling lamp, you see, headlamp. Now, I tested this recently, and it burns for several hours, 3 or 4 hours. It's a magnificent light. I'm just going to show, Oscar, can you just, I want you to show, can you see the green spot there? Can you see that? There are beautiful little jewels there, and on the side, you can see that. So as you're cycling along the road, people can see the bicycle with its, and these things are windproof as well. You know, as you're cycling along, you can imagine this, and the drafts, etc., they're draft proof. Very, very beautiful, and it's quite a powerful light as well. So this lasts for several hours. So if you run out of electricity, you have one of these at home, you see, and all your batteries fail, this will keep your illumination. This is a significant stage up from, I'm sure you all will agree, from the illuminating gases of earlier. Have we got the miner's lamp going? The miner's lamp as well. Now, this is the miner's lamp, also a fantastic, fantastic source of flame, etc. Now, I'll come on to the miner's lamp. It's not such a brilliant idea, and I'll explain why in the meantime, for the miners. And I'm hoping that some of you will know in anticipation. We can leave these 2 here for a while. And Oscar, could you now, in the darkness, set fire to one? Could you separate them apart slightly, Oscar? Thank you very much. One of the safety hazards always, when you ignite something which is flammable, make sure that other flammables are far away. So just set the other one further from the candle, Oscar. That's it. So watch the flame. Now notice the huge amount of smoke. For the second one, we'll have the lights on. You can see the flame there, but not the smoke. But the second one, we'll look at the smoke. Now, I do have to say, can you move it away a bit further from the candle, Oscar? Thank you very much indeed. This is purely for the visual effect. Thank you, Oscar. There we are. And now look at the black smoke. Now that you see, acetylene is a carbon-carbon with triple bonds in it, and that is what is unbelievably smoky. And so you're saying we're burning acetylene here with incomplete combustion, but these lamps don't produce any smoke at all. They are quite or minimal amounts of smoke. Why is that? Because they have brilliantly designed jets inside, which allow air to go in. Just as all your gas cookers at home, they burn with a blue flame. Why? Because the engineers have designed brilliantly, and woof, that's okay. We'll just, it's no deal. We'll just put it off. I think the flame, as I said, we haven't practiced with these. The point is that we should turn the top down once you've got the flame. It's of no concern, as you see, everything is in order, and we should turn it off, and we'll continue to burn. So if you're cycling along, you see, and suddenly you get extra illumination free of charge, and a rapid response, and we're back to square one. So thank you very much. So we continue, and we continue to do these things. Now, as I was saying then, why do we get this fantastic flame with no smoke? And the reason is because the jets, which I looked under a microscope recently, they have tiny little holes in them, and they allow air to go in. And that then gives you a flame of maximum luminosity, but with minimum smoke. They've been carefully designed. It's not just someone messing around. It is careful engineering and science put into practice. Now, the next thing I wanted to tell you, and this is we're now leading on to something much more serious, and that is working in mines and the mining and the history of mining. Coal has been mined, as you know, for a very long time, and I wanted to show the next slide, please, because I'm hoping it shows. I wanted to tell you something about miners in general, and the fact is that mining is definitely one of the most dangerous of activities, the most dangerous job you can possibly have. If some of you noticed some magnificent music of a choir singing at the beginning of this, and you wondered, have I turned up to the right place? Am I in the right department? Yes, you have. You had one of the world's greatest choirs singing, which was Welsh miners' choirs. The Welsh miners had a fantastic tradition of choral music, and they were among the best in the world. Mining has a very long history. It's the most dangerous job in the world. And during the first half of the 19th century, 1,000 people died annually working in coal mines. In the history of mining, children as young as 5 have worked in coal mines. Whole families, a whole community, the structure of society was built around coal mines. And that tradition continues today in many countries around the world. People often take their coal for granted. I remember when I grew up in Shepherd's Bush in the 1950s, every week the coal man used to come around. We used to have coal, used to put it in the coal cellar. But it's thanks to and I wanted to say, it's the coal mining industry that was the backbone of society. Thanks to coal miners, we had the Industrial Revolution. I'm not going to go anymore. May I warmly recommend the visit to one of our coal mining museums. I've personally visited National Coal Mining Museum in Wetherby, in Yorkshire. Phenomenal experience. You'll be amazed how much you can learn. And to recognize, I just wanted to quote the great wartime leader, Churchill, who was addressing miners on October the 31st, 1942. This was in the war at the time when things were very bad, morale was low, but things were beginning to change in the favor of the Allies. We shall not fail. And then someday when children ask, what did you do to win this inheritance for us and to make our name so respected among men? One will say, I was a fighter pilot. Another will say, I was in the submarine service. Another, I marched with the 8th Army. A fourth will say, none of you could have lived without the convoys and the merchant seamen. And you, in your turn, will say, with equal pride and with equal right, we cut the coal. So I'm just making the case that this industry and the history of mining is one of the most noble histories in the whole of the human race. It gave rise to communities, etc. Back to acetylene. Now, the dangers of working in coal mines, apart from the fact that the mine could collapse on top of you, were explosions. And so far, we have just seen gases burning with no explosions at all. But I now wanted to show you a couple of examples of explosions. Now, when do explosions occur and why do explosions occur? Well, it is because the gas which you are burning has been pre-mixed with oxygen. That is the simple rule as that. So if you pre-mix your fuel with air or with oxygen, it will burn completely differently. Now, we have an example of this every day in all internal combustion engines. When we drive our motor car, there are miniature explosions all the time going on inside the cylinders of our engine. Andres is now going to demonstrate 2 explosions, and one of them is where we have coal gas, which is, where's the one? Here, this, you see, this here is filled with methane. Methane, this is not coal gas, this is methane, natural gas, and that is the gas which was dreaded by the miners. This gas was called fire damp, and it wreaked havoc among the miners. Now, so when it burns on its own, it's not a problem, but when you mix it with air, it can make the most almighty bang you have ever heard. So Andres is going to light this. Let me explain it. This is full of pure methane, pure coal gas, pure natural gas. There is a small hole at the top and a big hole at the bottom. When he lights it at the top, it will burn with, you'll just see a flame coming out like pure gas burning. But as the flame burns, air will creep in at the bottom. And as air creeps in at the bottom, there will eventually be formed a mixture, which is an explosive mixture. And that explosive mixture will make quite a loud bang. Now, I will tell you when to put your hands over your ears, because this takes about 5 minutes. So we know from experience. Is that right, Andres? Thanks. If you could start that one off. And then, is this one primed yet? Not yet. We'll get this one going first of all. Now, I will very quickly talk about coal tar in the meantime. And coal tar, this magnificent mixture of substances. And now, that is now burning. Now, please watch. This here is pure methane burning. But as it burns, air is being drawn in through the bottom. So you say, that's nothing. That's just like a candle flame. Yes, it is. But the mixture is changing. The mixture of the gas in there is changing. Gradually, that flame is going to get smaller and smaller, and then it will almost disappear. It will go inside. And then suddenly, you'll get the effect of it, etc. So tell us, Andres, tell me when we should get the children to put their hands over there. It's not that, but it's a fairly loud bang, and you can observe what happens.
Once you don't see the flame, then that's...
Okay, as soon as you don't see the flame, children, put your hands over your ears like this, okay? So that's one there. Now, here we have a toy cannon. This is called a carbide cannon, and it's the exact, but this is acetylene mixed with air. Here it's methane mixed with air, here acetylene. So the rule is, for making an explosion, you need a mixture of a fuel with oxygen pre-mixed. If you don't premix them, they won't explode. Now, I think we're getting pretty close to that. I think from the moment you don't see the flame, it's still a couple of minutes. Are we ready to go with this, Andres? Are we ready to go with this? Now, I'm then going to turn on to, once this is happening, I wanted to turn on to, while this is all happening, I think I'm going to carry on talking because I don't want to carry on. And are we ready for Oscar to come and fire the cannon? Now, this too makes a bit of a bang. And now, let me see. Let's just explain. In here, in this cannon, Andres has put a small quantity of calcium carbide, and there is some water present. And that is reacting to make a tiny amount of acetylene. It's a very small, 0.1 of a gram. You can barely see it. But by gum, when that's mixed with air, it does make a little bang. So children, hands over ears. Oscar will now set this off by impacting the plunger. Yeah, hits it with your fist. Hard. There it was. Well, it wasn't that loud a bang. Can we try again, maybe? Maybe we waited for... I don't know what happened, so it doesn't matter. But this one will, and I think we're getting fairly close. We're getting fairly close, and we'll just have another quick go at that. Now, in the meantime, while we're waiting for this, there it was, so... And there we are. Well held, sir. I think this is for a cricket team. I think I must apply to be a cricketer. Now, please, are we to tell us when we're ready? I will continue. Can we have the next slide, please? The next slide, please. Now, the next slide tell us a little bit about the substances made from coal tar. The substances made from coal tar can be briefly divided into primaries, which are those listed there. Now, the benzene, toluene, naphthalene, anthracene, and phenol. Are we ready to go? Oscar's going to have another go. Hopefully, we'll get a louder bang this time. We've done before. This, by the way, we accept no responsibility. We didn't invent this. Is a commercial toy. So, Andres, I think we know what to do with this commercial toy. But it has always worked in the past, I have to say. So it's a little disappointing. Not to worry, we did have one successful one here. Now, on the subject then of the substances which you get out of coal tar. And this is the clever bit. From crude oil and modern hydrocarbon sources, we get primarily aliphatics, substances which contain single carbon-carbon bonds. But out of coal tar, we have substances which are primarily aromatic. This is a molecule of benzene. I'm not going to go into detail of the chemistry, but the pink and the purple represent chemical bonds. The important thing which represent delocalized orbitals and all the rest. But from a children's point of view, the formula for this is C6H12, 6 black ones and 12 hydrogens, which are the whites, and every carbon has 4 bonds. Here, it's a flat molecule, and this is a molecule of benzene. You may be interested to know that benzene was first discovered in this precise building by the great Michael Faraday, who was examining, incidentally, you've guessed it, illuminant gases. They did all sorts of experiments. Michael Faraday distilled whale oil, believe it or not, which they were investigating. He separated the products by fractional distillation, and using combustion analysis discovered the substance which he called carburet of hydrogen, by the way, had a formula C6H6, and that sample is present in this building. You may like to go and look for it. But this type of compound and opened up a totally new branch of chemistry hitherto unknown, and it all comes from that horrible black mess in there, which is coal tar. So when you distill coal tar, you get those which are called the primaries, and benzene, toluene, naphthalene, anthracene, and phenol. Now, the first 4 are hydrocarbons, and they all contain a benzene ring. The last one, phenol, contains an OH group, C6H5O. Have you heard of coal tar soap, used as an antiseptic? Today, still used. Coal tar, that word has survived to this day. And through intermediates, those have been manufactured a remarkable range of substances, as you see, which are listed up there. And there are loads of other substances as well. There are whole books and volumes written on the remarkable substances obtained from coal tar. Could we, Andres, just have a look at Andres has got a sample of anthracene, which is fluorescent. Would it help if we had the lights off? This glows in the dark if you shine a torch. So we'll just have a look. It's a fluorescent substance, and there you see it fluorescing in the dark as a torch is shown. And that is just one of the many, many properties discovered from the substances which are extracted from the fractional distillation of coal tar. But now I'm going to move on to dyestuffs. Dyestuffs, by the way, were first discovered by a remarkable accident. William Perkin, a brilliant young chemist, he's only 18, by the way, so listen, at the age of 18, he was investigating, and he was trying to produce quinine, I believe, and he was oxidizing it with an attempt to make something else. But in fact, he ended up with a fantastically colored substances, which subsequently became as Perkins mauve. That was 1856. That totally revolutionized the dyestuffs industry. And so, in other words, dyes which until then had been obtained from plants and from animals, now they were being able to make them synthetically. This here is aniline blue. That's a dye made from coal tar. This here we have is aniline yellow, and this here is rose aniline, which is a beautiful purple color. Now, rather than showing you samples, allow me to show you the remarkable collection. Could we have the nice next slide, please? Look at all of these dyes. Now, this is a wonderful range of colors derived from coal tar. This is, by the way, reproduced by kind permission of Dr. Alessandro, Alessandro, the curator of the Royal Pavilion in Brighton, because she actually collects these diagrams, and they are and you can just see all those colored dots, children. Don't bother with the chemistry below. Just look at all those colors from here. That's the remarkable fact which I wanted to alert you to. Now, we're turning to the final topic of the day, and that is photography. And I'm going to show you, could we start bringing on the equipment, please, for the photographs now? And I'm going to show you, to tell you that photographic chemicals, and you saw perfumes, explosive. That would require 5 or 6 separate talks to explain all of this, but such were the remarkable achievements of organic chemists in the latter half of the 19th century, that synthetic organic chemistry combined with analytical chemistry enabled us first to separation, first of all, by fractional distillation, identification by combustion analysis, and then synthetic routes, making a whole new range of substances. And synthetic organic chemistry continues to this day to make remarkable products. By the way, one of the ways of protecting yourself while they're setting up that, this, of course, is the famous miner's safety lamp invented by Sir Humphrey Davy in no other place than this building. This, of course, is one of the things and that he did. He was a remarkable man, gave lectures here and all the rest of it, one of the greatest scientists of all time, together with Faraday in this building. Now, the safety lamp essentially works on the principle, I'm not going to ignite it now, you burn a flame inside, and if you go into an area which is potentially explosive, then the wire gauze here allows the air to go through, but not the heat to go out. So the flame will turn color. The miner will then be warned that there is a methane around or fire damp, and they will be able to move away from the area. This, of course, thousands and hundreds of thousands of these were produced. And if you go to the National Coal Mining Museum in Wetherby, you'll see a whole cupboards full of them. And this is the point I'm coming to. Isn't it extraordinary that the miners used this to protect you from flames and the flame to give you light? Such was the life of the miner, hovering between success of getting the coal and fatality of getting killed in the process. So that's why it has been described as one of the most dangerous jobs of all time. Now, coming to photography, one of the greatest crazes or the greatest discoveries which set off a craze in the 19th century was photography. And this photography stemmed from the fact that for hundreds of years people had noted that certain substances are sensitive to light, especially silver compounds. And it was Nicéphore Niepce, a Frenchman, who produced the world's first ever permanent photographic image in 1822. Now, what I'm going to do now is I'm going to use the chemistry of Niepce and the silver bromide, or reducing silver bromide chemistry, to actually try and take a photograph in here in this room. It's a huge challenge. I'm going to be using a traditional plate camera from the Victorian era. I'm going to be using let me just have my photographic plate first of all. Sorry. I'm going to use a photographic plate which I have in here, and I'll explain very briefly the process. Normally, when we used to make photographs traditionally, used to make them on negatives. So this was the first metal plates, then glass plates, and then plastic negative like this. Now, this cone's this is gelatin on here on this plastic, and it's sensitized with silver bromide. And all I want to tell you is this obviously is no longer usable because you have to store it in a dark room. But during exposure to light, the silver chloride, silver bromide, gets converted to metallic silver. I don't know any more about the chemistry of it, apart from the fact that one of the greatest challenges of chemistry with photography was to reduce silver ions to silver in the process of developing. And for that process, coal tar came to the rescue. There was a compound called, today it's called hydroquinone, today it's called 1,3-dihydroxybenzene, hydroquinone, which to this day serves as the reducing agent to reduce silver ions to silver during the development of a photographic plate. So I'm going to now ask it's a young lady who's been asked to come forward and sit in the chair, and we're going to take a photograph, and after that, Andres will do the final demonstration, if you can kindly start with as soon as we finish. So please sit here, my dear, and thank you very much indeed. And what's your name? Benedicta. We're deeply honored. Benedicta's putting, I have to tell you, slightly herself at risk, you see. She's going to be exposed to a bright magnesium flash. We are using traditional Victorian technology here, so none of this computer nonsense, etc. We're simply doing basic chemistry and physics. Now, what I've got to do, first of all, I've got to set up the camera and focus on Benedicta. Now, this will take a little while, and we're going to shine a torch. If we can have, just for a second, I've got to shine a torch, and I've got to focus. I have pre-focused it, but I pre-focused it on my daughter, and my daughter was just a little higher, you see. So we're going to now lower it for Benedicta. Please watch carefully. I have here a Gandolfi tripod. For those of you who are interested in photography, this is a very right close up. Can you just sign on Benedicta's face, please? Very close up. So the reason why I'm doing this is I need to be able to have a spot on. No, it's not much closer than Andres from the front. That's it. Yeah, a bit more like that. Now this we have to have as the technique for focusing on her so that I can get the image as pin sharp as I can. This does not guarantee, by the way, I'm not going to make a great photograph. It is the idea of doing the process, undertaking the process, and seeing that. Thank you very much. That's it. She's in focus as much as I can get it now. Now what we do is this. We now stop the lens down to give it a greater, excuse me, I'm going to walk in. Don't move. Don't move. You mustn't move, my dear. Otherwise, we'll go out of focus. Now, this is Victorian photography. Thank you very much. We're stopping it down to F8 to give a greater depth of focus. We're going to set off the magnesium flash powder here, which I'm going to shortly mix up, using a traditional Victorian technique. Let's just have this, sorry, thank you very much. I'm going to mix these up together. Now this is literally, it's a tiny amount. It's a tiny amount. It's 1 gram of magnesium powder with 0.3 grams of potassium chlorate. Now this is a flash powder. It's used in fireworks, and I can assure you they use much greater quantities in fireworks. But on the other hand, you're much further away. So for this range, we think this should be satisfactory. Now, can I call Clara to bring our reflective umbrella, please? We're reproducing a full Victorian photographic studio, and in this here, and I say the chances of it working are not very high, but I believe it's very important that we should give it a... So, what I've done, I've mixed my flash powder here. I'm going to move it a bit closer to Benedicta, who will get a blinding white flash in her face. But she'll be looking there, of course. We've given her safety. Now, is this about the right distance? I hope so. Clara, you're going to be holding here. Now, we're going to be using... a hot wire technique, which the Victorians used as well, so you don't flap around with burning splints, etc. But I tried this out this morning, and I had to try a few attempts. It didn't work. So if this doesn't work, we will then have to resort to the traditional way of heating it with a lighted splint. But this does make quite a bright flash. It's not that. Look, I'm going to put the plate in now. Now, this is the clever bit. In here, you see, I have a plate, and this is a seal. This is called a plate holder. And in here, I have a sheet of positive paper. So this is photographic paper. So obviously, when we have this expo, now there should be where's the lens cap to the camera? Excuse me, we're just getting, did I have it? Thank you very much, Dave. Thank you very much. We have a lens cap. The only exposure here will be made by the flash, you see, of the magnesium. I don't guarantee it will work, and I will ask you to operate it. That's the night to say it wasn't my fault. Now, what we're going to do is, I now have to put in, so I focused it. We now slide our plate in at the back here. We now slide our plate in at the back here, and then we undo the latch which prevents me from accidentally exposing the plate. And now we're going. So now we've got the lens cap on. So that means even though I'm exposing the paper, this is positive paper, as I say, which has got silver bromide on it, even though I'm exposing that to the camera. There's no light getting through the camera because we haven't set anything off. So I'm now pulling the plate out. By the way, if any of you have seen school photographs, they're still using this technique for very large photographs. Now, so we've now exposed the thing. I will now ask for the lights to be turned off. And we're going to blow the candle out, obviously. Now, you'll notice that even with the lights turned off, there is a surprisingly large amount of background light. But we do, that's fine, Oscar, that's fine. Thank you very much for helping. So, the next thing we do now is I'm going to take the lens cap off, okay? And we'll see whether, and press now hard. Don't look at it, anyone? Fingers crossed, if not, we'll do, there. So there it is. Right, thank you very much. Now, we quickly put the lens cap on. I now close this off. Thank you very much, Andres. And now we go to develop it. Now, Dave has set up a special, thank you very much, Benedict. I do not guarantee a result. No, I think Benedicta, yes, for bravery, award for bravery. Now, what we're going to do is under red light here, which is, which is the developer? This one. That's the developer. Thank you, Dave. We're now going to push in our film, and in a special darkroom, which Dave has created here, which we'll shove it in and see whether we can get an image. So, have we got the tongs, the tweezers? Very many thanks, Dave. So we keep our fingers crossed. For a result. So thank you very much. I can barely see. I don't know whether I've even got the right sheet of paper in, I have to tell you the truth. So useless am I. This is positive paper. I'll see whether it's this one or maybe it was the other side. I can't tell. But oh no, it was. This is the right one. Whether we've got an image. Is it? I don't know, is it the right way? Yeah, it's the right way. Yes, we see. Something is appearing. We can see some dark glasses. We can see a nice smile. And let's just have a look. It's slightly out of focus, and there is a slight amount of fuzziness, but I think no one will doubt that that is an image, you see, which resembles the very nice young Benedicta. You'll have this as a souvenir to take home. I'm putting it in fixer now, the way. I finished with the coal tar derivative. I'm now on to a fixer, which is basically ammonium thiosulfate. But we'll leave that there, and we'll now go to the last experiment of the day. So photography in action, thanks to coal tar. That's the point I'm trying to make. Now, for the very final experiment, we're back to illumination. Now, what I wanted to say, thank you, before is a few concluding comments, and these are as follows. We owe today's world, we owe a great deal to the energy and the chemistry which has for thousands of years been provided by coal. In the future, though, we will be grateful for other sources of energy, other sources of chemicals. Coal is not eternal, and there is a limited supply in our ground. The people who are going to be involved in that science and technology of energy and supplies for the future are among you here today, children. You are the future, and to you we shall be looking forward. Those among you interested in science and technology, you will have this fantastic role to play in society of helping the whole of humanity to survive with energy and with chemical resources. For our final experiment, which is to do with light, we're now back to illumination. And we have here the gas, which is the most common gas in coal gas, which is what we started with, illuminating gas, and that is hydrogen. And what we have is a balloon filled with hydrogen. It is the lightest gas in the universe. You may be interested to know that hydrogen was formally recognized by the great English chemist Henry Cavendish in 1766. Notice the late 70s, that's when gas, the chemistry and the physics of gases was being investigated. So what I'm going to do is this this, I have here a fuse which is made up of nitrocellulose, which will burn rapidly down there, and it will then go up the light, up the thank you very much indeed, Andres. So we're going to ask for light to be switched off, as they were at the beginning, but this time, hands over ears, children. This doesn't make such a loud bang, but I think it's well worth protecting yourself just in case. It's going to be a bright yellow flash going along the gutter and then up the wire and this. So, let there be light. So there it is. Thank you very much indeed. Thank you very much indeed. Thank you very much indeed for your kind attention. Thank you very much indeed for your kind attention. Thank you so much indeed, and I hope you won't.